Alright, let's do one more quick problem. This is going to be an interesting problem to work on section 5.2 operational amplifier voltages and currents. Now here is the problem. As you can see, it looks a little interesting. The idea is that we are supposed to find IA, that is the current flowing in this branch, okay, and then VA, which is the voltage here, find VA, and then we are also supposed to calculate, let's see, IO, the current flowing in the output terminal of the OpAmp, and then of course calculate also the output voltage here. Okay, so 4 terms that we need to calculate. So it's a little bit of a lengthy process. It's not complicated. It's simply an application of what we learned so far, but it's a little step-by-step lengthy process. Okay. As always, let's simply start by writing KCL at that node, Vn. Okay, and I'm not going to solve what we already know. I'm simply directly going to apply step 1. Of course, this is in negative feedback configuration, so we are going to assume the op-amp is in linear region of operation, and I'm simply going to skip that step. The other step is, notice that I'm directly going to apply Vp equals to Vn, that rule or the constraint. Vp is tied to ground, therefore Vn is 0. Okay, simplifying the analysis here, step 2, we start out by writing KCL at node Vn. Okay, Vn, there are 3 currents flowing in there. There's one current flowing to the left, there's another current flowing that way, and here is another current IN, which is really 0. The current going into the op-amp is 0. So if we write KCL here, Vn minus 240 millivolts divided by 8 kilo ohms, that is the amount of current flowing in the 8 kilo ohm resistance. Okay, plus what is the current flowing in this branch? That's simply IA, right? The current flowing in that branch is IA plus the current going into the negative terminal of the op-amp. That's this guy, IN, I sub n. Okay, we know that is 0. So I'm not going to waste any more time. I know IP equals to IN equals to 0. So I'm simply going to write that equation, that rule right there. Okay, so this guy is 0, this guy is 0. Okay, so simplifying this equation, I simply get IA or negative 240 millivolts by 8 kilo ohms plus IA equals to 0. So rearrange the equation, you get a value of IA equals to 30 microamperes. Okay, that's one of the first problems that we are supposed to solve. IA is 30 microamperes. Now, so that's the current going in the feedback branch. Okay, now we are supposed to calculate, so that's 30 microamperes. We found that out, 30 microamperes. Okay, 30 microamperes. Now the next step is to calculate VA. So what I'm going to do is to write node equation KCL at that node. Okay, sum all the currents leaving that node. Okay, when you sum all the currents leaving that node, what you get is KCL. So this is KCL at node VA. Okay, KCL at node VA. Now when you do that, the current going in the left branch is VA minus Vn over 60 kilo ohms. That is the amount of current flowing in this branch. Okay, now what is the current flowing in the 30 kilo ohms? Okay, the current flowing in that branch is simply, think about it, VA minus VO, because this voltage is VO, right? That's the VO voltage divided by 30K. Okay, so that divided by 30K. Okay, and there is a current flowing down which is VA by 40K. Okay, so there are three branch currents all leaving the node. I'm going to cut them and paste it over here. Okay, VA. Okay, you see. Then the other branch current is this guy. Cut that, paste it over here. Okay, so there are two branch currents that we have taken care of. So that's this guy and this guy. We still have to write the equation for the current going down. Okay, the current going down is simply VA by 40 kilo ohms. Okay, VA by 40 kilo ohms. Let me plug that in there. So VA 40 kilo ohms, all of that should equal 0. Okay, so we know the value of Vn, this is 0, right? We know the value of VA. VA is what? We just calculated, did we or did we not calculate VA? We can calculate VA. You know what? This is, we'll come back to this. Let's park this to one side because it's easier to calculate VA first. Okay, so I have the value for IA. Okay, I have the value for IA, and then we can apply KCL at VA, at node VA. Okay, once we apply KCL at node VA, okay, we calculated the value of IA to be 30 microamperes, and VA, now think about this, here The same equation, IA, we know the value of IA, which is simply, think about this, Vn minus Va over 60 kilo ohms. Okay, Ia is Vn minus Va over 60 kilo ohms, right? Because the current flowing in this branch is the voltage at this node minus the voltage in this node divided by the resistance over here. Okay, so we know the value of Vn. Vn is going to be 0. Okay, so we should be able to calculate the value for Va. So Va equals to Ia times 60 kilo ohms. There's a negative sign. Okay, so you do that, Va will come out to be 1.8 volts. Okay, so this is another result that we are after, 1.8 volts. Okay, so all we did was to look at the branch current IA. IA is nothing but Vn minus Va over 60 kilo ohms, right? That's what we did. Now let's go on to writing the KCL at node VA. We know the value of VA, which is going to be 1.8, which is going to be negative 1.8 volts. So let me fix that there. This is going to be negative 1.8 volts. Okay, because IA is 30 microamperes. Don't forget the negative sign in there. So that's that negative sign. So we know the value of VA. We can plug it in there. The only unknown is VO. Okay, so we can plug in the value of VA equals to 1.8 in this equation. If you want to call this equation 1, okay, call this equation 1. Okay, now plug in a value of VA equals to 1.8, and then you'll see that VO is actually negative 4.05 volts. Okay, see what we have done? We have applied the rules Vp Vn equals to 0, Ip In equals to 0 in the first step. The second step is KCL at node Vn. Okay, then the third step, step number 3, okay, step number 3 is simply applying the voltage difference divided by the resistance gives you Ia. Okay, so the voltage difference Vn minus Va over 60 kilo ohms gives you Ia. Okay, but we know the value of Ia, so we calculated that. Now step 4 is, step 4 is applying KCL at node VA. Okay, so let's see KCL. This is step number 4. Okay, and then we know the value of VA. We know Vn is 0. Therefore, we should be able to calculate VO to be negative 4.05 volts. Okay, so that's step number 4. Let's calculate VO to be negative 4.05 volts. Let's write that down. Okay, the only unknown now is I0 or IO. In order to calculate IO, what we do is step number 5. Is it step number 5 or step number 4? Step number 5. Step number 5, look what I'm going to do. Okay. So far, I have written KCL at this node, KCL at this node. Now I'm going to write KCL at that node. Okay. So pay careful attention. I'm going to write KCL at the output node. Okay. At this output node, there are 3 currents. There is one current going south, there is one current going north, there is one current IO going west. Okay, so here going south, the current going south is VO minus ground 0 by 20 kilo ohms. Okay, that's the current going south. Current going north is what? Current going north is VO minus VA over 30 kilo ohms. Okay, remember we are looking at this node and that node. The current going in this branch is V0 minus VA over 30 kilo ohms, and then of course there is the current IO going to the westward direction. Okay, so let's add those. Current going south is VO, remember VO over 20 kilo ohms, VO over 20 kilo ohms. Okay, that's this guy. That's the current going south. Okay, now the other current going north is this guy, VO minus VA over 30 kilo ohms. I'm going to cut that and paste it over here. Okay, let's just paste it over here. Okay, add that current, and let us not forget there is one more branch current going west. Okay, we are writing KCL at this node. We plugged in a value for plugged in an expression for current going south. We also plugged in an expression for current going north. Then there is this IO going west. Okay, so that completes all that includes all the currents leaving that node when we are writing KCL at that node. Okay, so plus I0, all of that equals to 0 because this is KCL at node V output. Okay, so this is an interesting problem because we are writing 3 KCL equations. First KCL equation is KCL at node Vn, then KCL at node Va, then KCL at node Vo. Okay, now if you think about it, you know the value of Vo. Vo is negative 4.05 volts. Okay, now you know the value of VA. VA is negative 1.8 volts. We calculated them in the previous step. So plug those in to equation 2. Okay, plug these values into equation 2. You should get a value for I0 to be 277.5 microamperes. Okay, you see the idea? So the only thing that's different here is we are using KCL a bunch of different times, 3 times actually. So 277.5 microamperes. Okay, so in order to solve this problem, it is a negative feedback configuration. what we did was to apply the rules Vp equals to Vn, In equals to Ip equals to 0. Then it's just a matter of applying KCL at 3 different nodes. Okay, the nodes shown in highlighted in blue. At each of those nodes, you apply KCL, and that will give us the 4 unknowns that we are trying to calculate.